Hello. We're going to go over this question, section 7.2. It's like number 10, but not exactly like. So you'll get some experience working on a linear programming problem using the graphical method, a little bit more difficult than the easiest ones in that chapter. All right, so, so here is the statement. I hope you can read this. So it says we're going to maximize z equal to x plus 3y, subject to these constraints. That 6x plus 3y is less than or equal to 180, 5x plus 4y is less than or equal to 200, x should be greater than or equal to 10, which is kind of different, and y should be greater than or equal to 20. So not just the first quadrant, right? So graphing the feasibility region is going to be the first step, right? Step 2 is going to be checking the counterpoint, the corner point theorem. See if we can use it. And then step 3, carrying through on that decision from step 2. Okay, so you don't always get to build a corner point table. You have to check. All right. But first, you have to see if the feasibility region is bounded by graphing it. All right. So, like I said, this one's a little bit more complicated because it's not just saying x greater than or equal to 0, y greater than or equal to 0. It's not just in the first quadrant. We need to know where x equal to 10 is and y equal to 20 is. Those are the boundary lines of that region. So if that's the first quadrant, then if I establish that this is x equal to 10, and y equal to 20, let's see. So if that's going to be x equal to 10, now on the y-axis I'm going to have a different scale, right? So if we make this y equal to 10, 20, 30, 40, here's y equal to 20, that's a boundary line. There's y equal to 20. They want x greater than or equal to 10. Well, that's going to include things to the right of x equal to 10, like 11, x equal to 11. And y greater than or equal to 20 is going to be things above, a half plane above that line. So instead of being in the first quadrant, at first we're thinking we're in this area up here. It all hinges on where the boundary lines of these regions are. So we're going to do our usual trick, come up with points that are on the first boundary line. Slightly different because we're not looking at x greater than or equal to 0, y greater than or equal to 0. I'm going to switch this up a little bit. For example, what happens when x is equal to 10? Excuse me. If x is equal to 10, where is that line going to intersect x equal to 10? So if x is equal to 10, that is going to be 60. 60 from 180 is 120. That makes y equal to 40. And you can, work that out a little bit a little longer. But you get the point that 1040 is on that first line. What else? Another good point to find on that first line is what to do when y is equal to 20. When y is equal to 20, what goes? So if y is equal to 20, then this term, 3 times y is 60, that's 60. 180 minus 60 is 120. 6 times what will be equal to 120? Another 20. You can verify. that the line that's the boundary of this region contains these 2 points. So I'll call that line 1. And I'm going to say line 1. I had a better choice of colors here. Line 1 contains those 2 points. So let me draw them in red. So we need 1040 and 2020. So if this is x equal to 10, all right, and there's another 10. So there's x equal to 20. And coming up here, when that hits 2020, that would be right here. So that first line looks like this. Now they said they wanted all the points where 6x plus 3y is less than or equal to 180. So that's below this red line, as I'm sure you've been getting used to. And for example, 0, 0 is on there, right? So it's this half plane, and yet we have to stay inside this special new little corner. How to pause. Just a minute. So for the other line, line 2 here, points that are on that are, for example, 2420. How did I get that? Again, by letting y equal to 20. Then I solve for what the x would be, 24. And another point that would be on here, the second line, is what happens when x is equal to 10. So if x is equal to 10, then this is 50. 50 from 200 is 150. If that was a 2, then we could say y is equal to 75, but we need to split that again, so that's 37 and a half. Fractions. So 24, 20 is going to be, let's see if that's another, that's 30. 24, 20 is going to be about there. And 10 and 37 and a half. 10, there's 30, 37 and a half is about there. So now I've got to join these 2 points in these straight lines, straight as I can draw right now. Something like that. All right, so what is in the half plane, what is in the region that is below this blue line and yet below that red line, yet above this horizontal line y equal to 20 and to the right of x equal to 10? It's this region right here. And so we have to figure out where those 2 lines L1 and L2 intersect. But you know how to do that very easily, don't you? Right? Using RREF. So L1 intersect L2. Where do these lines intersect? At the solution to 6, 3, 180, 5, 4, 200. In other words, looking just at these equations, where are those 2 equations simultaneously true? That's solving a system of equations, which is like equivalent to using RREF on this augmented matrix. Turns out that gives you something that looks like this, 1, 0, 0, 1. I just used our REF. This is what I would write on my paper, right? That implies our REF gives you 13 1/3 and 33 1/3. So those are the coordinates at this point right here. All right, so now I'm going to start labeling the corner points of the feasibility region. So that's my 13 1/3, 33 1/3. What was this one? Line 1 is in red. That's the 20/20 point. This is from line 2, when y is equal to 10. That's the 10, 37.5 point right there. And we need this one. What's that one? What's at the intersection of x equal to 10 and y equal to 20? I have the point 10, 20, of course. Okay, so now we have graphed the feasibility region. After you've graphed the feasibility region, then you can check the hypotheses of the corner point theorem. Remember what that is. Right there, page 344. Okay. Is that region bounded? Yes. So since it's bounded, we can answer either maximum or minimum. Okay. You gotta state that. All right. So part of your work is to look at this and say, so this implies feasibility region is bounded, and by corner point theorem, a maximum of z equal to x plus 3y exists at one of these corner points. In other words, you make a corner point table. Corner point table for maximizing z equal to x plus 3y. Yes, you build a table off of this. So we need for every x and y pair, we're going to need an x column, a 3y column, and then their sum. So here we're going to list the corner points, which are 10, 20, 10, 37 1/2, 13 1/3, 33 1/3, and 20, 20. Okay, so you list all the corner points next to your diagram showing them, and then you start filling out the table. So what are the x values at these points? Well, they're the first coordinate, 10, 10, 13 1/3, and 20. What are the y coordinates? Sorry, not what are the y coordinates, but it's 3 times the y coordinates. So this y coordinate is 20, 3 times that is 60. 3 times 37 1/2. 37 1/2 plus 1/2 multiplied by 3. What does that give us? 1, 2, 9, 11 plus 1 1/2. That's 3/2 is 1 1/2. So that's 112 and a half. Let's see, what's y here? 33 and a third. Well, you multiply that by 3 and you get 100. If y is equal to 20, 3 times that is 60. So you fill those in, and now this last one says x plus 3y. So you just add those. 70, so z would be 70 at that point. At 10 and 37 and a half, it's 122 and a half. That's happening right there. At 13 and a third and 33 and a third, that's the neighborhood kid, sorry. 13 and a third and 33 and a third, the value will be, let's see, 113 and a third. And then here, that adds up to 80. So, if we're maximizing z, which corner point does it? This one. And so that means that this is our action plan. We should let x equal to 10, y equal to 37 and a half to get the maximum value of z possible, 122 and a half. Now you should write all that up as a sentence ending your problem. So I'll do that here. So after all that, here's our conclusion. Our neighbors are right next door. Excuse me. Excuse them. So let's see. When x is equal to 10 and y is equal to 37 and a half, the maximum z value is 122 and a half. And that's the end of that optimization problem.